In this section, we are going to be looking at limits that are approaching infinity, both positive and negative, and relating those to a concept we already know about, which is asymptotes. We'll start with the formal definition of a limit. This is similar to what we've had before. The only difference is that instead of approaching a particular number, like 2 or 3, we're having the x values approach either positive infinity or negative infinity, and we want to determine what's happening to the function values, the y values, as x approaches positive or negative infinity. We still have the same idea that the function is within an epsilon neighborhood of the limit whenever, in the case of approaching positive infinity, our x's are beyond some number, right, going towards positive infinity. In the case of negative infinity, our x's are below or less than some number as we're approaching negative infinity. Here's an example of common function that you've seen before, y equals 1 over x. What we're saying is that, let's first talk about the side where x is approaching positive infinity. I have some number that I've chosen, m, here. And I'm saying that as I move more towards positive infinity, beyond, if I choose x values beyond m or greater than m, that I'm closing in on this smaller and smaller epsilon window. I can see here it's getting smaller and smaller as my x values get larger. Similarly, if I were to look at the case where we're approaching negative infinity, I'm choosing some number n, and anytime I choose an x value that is less than n, this epsilon neighborhood, so to speak, is getting smaller and smaller as our x's move towards negative infinity. And so because those spaces are getting smaller, we can say that the function is approaching, in this case, the x-axis, or y equals 0. Now, we will use the same limit laws that we had before, where we can add, subtract, multiply, divide different limits, multiply by a scalar number, when we have limits that are approaching positive or negative infinity. So in this first example, we're looking at the function 5 plus 1 over x. So it's similar to the function we're just looking at, but that 5 is going to shift the graph up 5 units. The limit laws that we had before said that we can separate the function 5 and the function 1 over x into 2 separate limits. So you see that we do that. And then that allows us to use the fact that when we have a constant function that, and as the limit's approaching infinity, that's just going to be, oh, this is switched, right? This should be 5 for this one, and it should be 0 for this one. So the first limit, because it's a constant function, y equals 5, like this. This is the function of the first one. As we go out toward infinity, the function value is always going to be 5. And so when we add these two limits together, we get 5 overall. Looking at the second function, we've got pi times the square root of 3. That's also a constant function, right? Pi is a number, square root of 3 is a number. So when we evaluate that at infinity, we're still going to just get the function value as the output. And then we've also got 1 over x squared. The 1 over x squared in this case has been separated into 1 over x times 1 over x. Each of those individual limits goes to 0. So that's what you're seeing here, 0 times 0. So overall, this limit is going to be approaching 0 because the 1 over x squared part is really driving the y values, and that number pi times the square root of 3 in the numerator isn't having a very big impact on the overall graph. The most common functions that we see, asymptotes or limits at infinity, happen with rational functions because we know there are restrictions on what we can enter into the domain. We don't ever want the denominator of a function to be equal to 0. So if we look at this function over here on the right, in the upper right-hand corner, we can figure out that we have a horizontal asymptote at this point. As the function goes out towards positive infinity here, I see that as x goes out to positive infinity, the function is getting really, really close to this line y equals 5/3. And then similarly, as the function over here goes towards negative infinity, the function's also closing in, but from the bottom side to 5/3. To see that mathematically, over here in example number 1, what we're going to do is divide every single term by the highest degree of the variable. In this case, that's x squared. So I started with this first term and divided it by x squared to get 5. And then I divided this term by x squared to get 8/x, and so forth. I divide every single term in the rational expression by x squared, and I end up with this second iteration of the function. And because we know that 1/x and also 1/x squared, any time that I have a power of x in the denominator, these are all going to approach 0 as x goes to either positive or negative infinity. What's happening is I'm plugging in really, really large values for x. And so when the denominator is a big number, the overall fraction is incredibly small. And so that's why we're saying that these approach 0. So to analyze what's happening with the function, I can take all of these values that are being highlighted, say they're effectively going to go to 0. And so the only numbers that are really deciding what's happening with the y values overall is the 5 and the 3. And so that's how we get that horizontal asymptote at 5/3. Number 2 is a similar type of problem. In that case, the highest power is the x cubed. So you see that we've divided each of the terms by x cubed. And in doing so, we have 3 of our terms that are going to end up going to 0. So we end up with 0/2, or just 0 as a horizontal asymptote. And then we've got the definition here of horizontal asymptote, which is saying that the y values approach a particular number as x goes either to positive or negative infinity. Here are a couple of unique examples, different to ones you may have seen in the past. The first one is interesting because it actually has 2 horizontal asymptotes in the same graph. You can see that one is approaching from the bottom here, and then this other one's approaching from the bottom here. So this is just kind of an interesting graph in the way that it's got these two asymptotes. For the second graph, you've probably seen the exponential function, y equals x, or e to the x, and the y values approach 0 as x goes to negative infinity. So in these first two examples, we're getting those horizontal asymptotes just either only from one side. It doesn't have to be from both sides of the function that are approaching the same value. And then this last one, x times the sine of 1/x, is a really cool looking graph. It's got the line y equals 1 as a horizontal asymptote. Here where I have 2 plus sine x/x, you can see that the function oscillates up and down, zeroing in or closing in on the line of, in this case, y equals 2. And this example is brought up to show that you can have the graph cross an asymptote. That's okay. But it's still, as we go out towards the extremes of positive and negative infinity, it's still closing in on that horizontal line. Some of you in pre-calculus may have seen oblique asymptotes. That's when you have an asymptote that's at an angle. It's not parallel to the x or to the y axis. The way that we find oblique asymptotes is by using long division. I'll just show you how we did that here. The original function is here. It's x squared minus 3 over 2x minus 4. So to find the equation of the oblique asymptote, we would take the divisor and divide it into the numerator here. Remember that when you're doing long division, you have to leave a space for all the possible powers of the variable. So I'm going to add in a space for x to the first power and then minus 3. And then I ask myself, what do I need to, what do I need to multiply this by to get x squared? And the answer is going to be x divided by 2. And I write that in the column where I've got x to the first power. So I'll put x over 2 here. Then I'm going to multiply down. So I'm going to have x squared minus x over 2 times 4 is going to be 2x. And then we subtract, right? So in subtracting, this becomes negative and this changes to positive. So I'll have a 2x minus 3. We repeat the process. 2x, I need to multiply by plus 1. And then I've got 2x minus 4. This changes to minus, this changes to plus. And so I have a remainder of 1. The remainder doesn't matter in this case, but the part that matters is what we get as our quotient. And so that becomes the equation of the oblique asymptote, you can see here. As we choose x values that are going out towards positive or negative infinity, the distance between the function, which is the blue line, and the oblique asymptote, that goes to 0. Okay, let's go back. Okay. Here are 2 different examples of infinite limits. A couple of things, a couple of notes I want you to see. First of all, the one on the left, the picture on the left for 1 over x, as we choose x values that are closer and closer to 0 from the positive side, so going this direction, the function values are shooting up to positive infinity. On the other side, as I choose x values that are closer and closer to 0 from the negative side, the function values are shooting down to negative infinity. So we would say that the one-sided limits exist, right? The limit from the right or the limit from the left, but that the limit overall does not exist because they're not approaching the same infinity value. Whereas on the right-hand side, I can see that as I approach 0 from both right and left, the entire function is going up to positive infinity. So I would say that the limit approaches positive infinity. Now, just some semantics. Because infinity isn't a number, we are really just talking about a conceptual idea that as the x values approach, in this case, in both cases, 0, the function values become arbitrarily large. And so we're saying they're moving in the direction of infinity, positive or negative, whatever that is. But we're not really saying, oh, it's going to reach this limit and that limit is infinity, because infinity doesn't exist. I know, just a little math nerdiness, but I just want to point out that we're really just saying that the function values get very, very large or very, very small. So here's the formal definition of an asymptote, a vertical asymptote, that is. That as the function approaches a particular number, a is the one there, from both the right and the left, the function values go to positive or negative infinity. So in this first graph, we can see that as the function values approach 2 from the right and from the left, on the right-hand side, the y values are going to positive infinity. On the left-hand side, the y values are going to negative infinity. So we say overall that there's an asymptote there. We don't even really need to talk necessarily about the limit. We're just using it to determine where asymptotes are. And in using division again, we're able to get this number here, 1, y equals 1, and that gives us the horizontal asymptote. Or some of you might know that when we're trying to determine, we know that horizontal asymptotes exist when the degree of the numerator and the denominator is the same, and it ends up that the asymptote ends up being the coefficients of the leading term. So in this case, it was 1 divided by 1, and that's how we get that horizontal asymptote. I kind of alluded to this a little bit before looking at the second graph, that for something to be an asymptote, it doesn't the graph doesn't have to approach that line from both sides. So here we have the x-axis as a horizontal asymptote, even though the graph is approaching that line only from the bottom. It's the top of the graph doesn't come in and approach y equals 0, and that's okay. If the graph is approaching from any one direction, we can say it's an asymptote. And then the third example is just worth noting. We've got these inverse functions of one another, the exponential function and the natural log function. Because inverse functions have x and y values exchanged, we get this x-axis as an asymptote for the exponential function and y-axis as an asymptote for the natural log function. And then final slide, we've talked about this a little bit already in class, but we have trig graphs are the best example of functions that have infinitely many asymptotes, vertical asymptotes in this case. All right, thanks for watching, and I will see you in class.